Assalamu alaikum. This is going to be the first lecture of Module 3. So far, we have covered the contents of Module 1 and Module 2, and with the continuation of which Module 3. In our very first class, the introductory class, I have provided you the course plan, and if you look at the course plan, you will have an idea what we are going to discuss in this Module 3 or the lectures of Module 3. Okay, let me give you an overview. We are going to learn about the mathematical equation that dictates any LTI system and how that can be used in practical cases. That is the main focus of our modules. Before we begin, we have to go through that the cliched topic or the term that we have seen quite a few number of times in this course, that is linear time invariant system. Okay, so what is a LTI system or linear time invariant system? A linear time invariant system is a system which has these both properties, one linearity and another one is time invariance. What do we mean by the linearity? It means that the system should follow the superposition rules. Okay, I believe by now you already know what superposition rule is, as we have discussed this in our previous lectures. And what is time invariance? Time invariance is that if we have a system and we are providing some input to the system, and correspondingly we will have definitely some output. If we make some time shift in the input, let's say if the input was here and we have shifted the input to the right by t naught, if the system is time invariant, in that case the output will also get shifted to the same amount of value to the right. If that is what happens to a system, in that case we can call that system to be time invariant. And on top of that, if that system also fulfill the superposition rules, we can say that that system is a linear time invariant system. Okay. So what is the very common example of linear time invariant system from our electrical engineering perspective? That is electrical circuit that we have already discussed so far. So if we want to look at it from a very practical scenarios perspective, is that uh, imagine any sort of circuits that you see around you. Uh, we can name the fan that we have moving above our head. That is basically a motor. If we convert it into basic circuit, that will be an RLC circuit. Let us look at some of the amplifiers that we are using for our electronic devices. If you break it down properly, that will convert it into an RLC circuit. So as a whole, we can see that the most of the practical circuits that we use for our day-to-day use can be simplified into this RLC circuits form. And again, these RLC circuits are obviously are LTI systems. So this translates into this that most of the circuits we use in our day-to-day life are necessarily RLC circuit, and RLC circuits are mainly linear time invariant systems. So if we can figure out the mathematical equation that dictates the operation of RLC circuits, we can say that we have figured out the mathematical equation that dictates the operation of LTI systems, right? And once we have that mathematical equation chalked out, we will see how we can use it for our own benefit. Okay, now let us look at a circuit here that is the very basic RL circuit here given. So if we apply the KVL in the circuit, the current is going in this loop. So we will come across these three voltage entities, that is one voltage drop across the resistor, one voltage that will be involved with the inductor, and obviously the source. If we translate this into KVL, so this is what the equation is. I think you all will agree with this mathematical equation. Now, here in this circuit, we can see that the battery or the source that we have used can be considered as input, obviously. And another time varying uh, entity that is involved with the circuit is the current. So we can consider that current is our output. Now that we have considered that the working principle of this RL circuit can be defined by this equation, and we have taken this decision that we will replace the voltage as it is the input to this system. So we will replace it by xt, and the current that is involved here, we are considering it to be output of the system, and we will replace it by yt. So if we bring these two changes in this equation, that results in this. So now this looks more like a differential equation, and that is first order differential equation. And from the basic mathematical knowledge we have, we obviously know that if we solve this equation, we can calculate the yt, and if the nature of xt is given to us, we can calculate the yt more precisely. Okay. So the thing is that the mathematical equation that is governing the relationship between the input and the output of the system is necessarily a differential equation. So we can come to this conclusion that if we have an RL circuit in form of an LTI system presented to us, in that case we can say that the operation of that LTI system is governed by this mathematical equation, and this mathematical equation is a differential equation, or if we want to specify it more specifically, then we can say that this is defined by a first order differential equation, right? We can look at few other examples like an RC circuit. For RC circuit, the situation is also the same. If we have an RC circuit given to us, there we get to see two voltage entities coming into play. That is one voltage across the resistor, one voltage across the capacitor. And if we apply KVL, this is the equation we are going to get. Then if we differentiate this equation, we get this as a result. So like the previous case, if we consider the voltage source as input and replace it by xt, and consider it as output and replace it by yt, in this equation, that will give us this output, which is also a differential equation of first order. That means if we are given an RC circuit, which is a very practical electrical circuit, which is also an LTI system. So the equation that is governing the working principle of this system is a differential equation, right? There is only another variation of RLC circuit is possible, that is both RLC. All the three components are available in a circuit. So if we make all of them available in a circuit, in that case we come across four voltage related entities. One is the source, one is the voltage drop across the resistor, one is the voltage drop associated with the inductor, another one is the voltage drop associated with the capacitor. So if we convert it using the KVL, this is what we get, and by differentiating this formula, we get this thing. So here we have bring uh, this quantity here and move this over here, and this the position of this part is uh, unchanged. So there is a mistake maybe. So this should be there should be an integration sign. So that was the equation. So if we again replace voltage as input and replace it by xt, and if we again consider it as output and replace it by yt, so we will get to see a differential equation of this type. And if we rewrite it or rephrase it, it takes a form like this. So this is a second order differential equation. So which translates into the same thing, that if we are given an RLC circuit, that RLC circuit is a very common practical electrical circuit, and the equation that is governing the working principle of this circuit or this LTI system is a differential equation. So the point that I'm trying to make is that any LTI system is governed by its differential equation. So LTI systems has another characteristic that their input output relationship or their characteristic can be defined by a differential equation. And there is another catch to it that if you look at the differential equations that we have derived so far, all of them has some coefficient, but these coefficients are basically constants. Why? Because in a circuit you know the value of R and you know the value of L. So these are all specified value. So if we are building a circuit, we will define the value of R, let's say 10 kilo ohm, and the value of L is 1 macro mH. So in that case, we can say that the value of the R and L are defined. So these are constants. In this way, again, if we have RC circuit, the value of C is also defined. So this is also a constant, this is a constant. And for RLC case, we can say that these are also constants. So that means that any LTI system can be defined by a constant coefficient differential equation. That means the coefficient that will be associated with the differential equation will also be a constant. So that is another parameter. So the final point that I'm trying to make is that the working principle or the operation of an LTI system can be defined by a differential equation, constant coefficient differential equation. So that constant coefficient differential equation should have a generalized form. So far we have seen it for any RLC circuit. So for any RLC circuit, the constant coefficient differential equation looks like this. And if we convert this one into a generalized form, this is how it looks like. So we have the highest order differential operator and then differential operator with one order less than the highest one, and in the ascending order the last term of the output is not associated with any differential operator. And look at the coefficient, it is increasing one by one, and for same for the input case. So here we had only three terms, so we have defined it in this way, but the defining differential constant coefficient differential equation of an LTI system is not should there are no hard and fast rule that it should be bound with only three terms. There can be multiple terms. So for multiple terms, the general form should look like this. See, this is how it looks like. And for the input case, the same thing is repeated, but the value of the coefficient is replaced by in place of a naught. Here we have written b naught, and the order for the differential operator order in place of n, here we have written m. So that is the only difference. So the main thing is that the LTI system, the defining the defining equation of an LTI system is a differential equation, and that differential equation has this basic format. So the discussion that I have had so far, in conclusion, it can be said that the defining mathematical equation of any LTI system is a constant coefficient differential equation that has a generalized version like this. And if this is the generalized version, in that case, we can say that n is the order of the equation. If the value of n is 2, then it is the second order differential equation. Likewise, we have seen for the case of RLC. And the value of n should be greater than or equal to m. So for our RLC case, we saw that it is an output case. It was d square by dt square yt, and for Input k was d dt of xt. So the value of n there was 1 and value of n there was 2. It fulfilled the criteria, and also the coefficient a0 must be 1. So for our differential equation that we derived for RLC circuit, there the value of a0 was also 1. So the bottom line is that mathematical equation that governs the operation of an LTI system is a constant coefficient differential equation, and it has this generalized form, and this generalized form has some rules associated with it. If these are followed, then we can say that this is one differential equation that is representing an LTI system, and by solving that differential equation, we can predict the nature of the output of the LTI system.